The next talk should be given by my collaborator, Tjerk Straatsma from Oak Ridge. He wasn't able to travel after we initially planned. But I'm collaborating with him. So the title is Enabling Large-Scale Science on Summit with Highly Efficient Scientific Applications Developed through the Center for Accelerated Application Readiness, or CAR. So this is our progression, Jaguar, Titan, Summit, and then on to Frontier. Right now, Summit is the focus of most of our technical efforts. So, yeah, I can show this. There's our picture of the Power 9 processor. This particular image was not shown this morning. It has up to 24 cores. The Coral machines have 22 cores for yield optimization on the very first processors. And it has a PCI Express 4, which was quite novel and attractive, NVLink 2, we're using the version with the 4 hardware threads, right? That's the P9 that we're getting. And here's the NVIDIA Volta. It's a very strong GPU. I would say, you get nice percentages of increase in the performance and the peak performance going from Pascal to Volta. The memory management on the Volta is very much improved, and actually, so you should expect to get higher percentages of peak from the Volta than you saw on the Pascal. Of course, what's new and was actually surprising to us when it was announced about a year ago are these Cuda cores for doing reduced precision analysis. That was not something we knew about in the procurement, but it added new focus and new interest to the project that we were executing. Just the same way Adam indicated, we had an early access system that we call Summit Dev. It's 3 racks of 54 Minsky nodes. We've had it for about 1.25 years in order to work on application development. So there's 2 Power 8s plus 4 GPUs, Pascals per node, connected by the version 1 of NVLink. There's 4 racks shown here. The 4th rack was given to the system development experts, the HPC operations group, in order to test their hardware and work on file system development and related activities. So when we execute a project like this, sign the initial contracts, we begin working straight away on the applications. So we did a call for application readiness projects. We initially budgeted for 8 of these projects. We had budgeted for 6 in the Titan project, but we got 29 proposals. And we considered 28 of them to be excellent. The 29th one was the one we got in 2014 on machine learning. And it was immature. Even the PI of the project said it was immature. That shows you how quickly our community is moving, I think, from the beginning of this project to where we are now. And so we expanded the number of projects, added budget, added effort, and accepted 13 of these application readiness projects. And these were part of the activity of the Center of Excellence that Adam mentioned, where we're working together with Livermore and IBM and NVIDIA experts on understanding, making a plan for how these applications are going to be readied for Summit, and then doing the work on a regular basis to move them and get them ready for Summit. First on Summit Dev, and then on to Summit now. Our goals include, for sure, early science achievements. We want applications to begin being very productive very early in the life of our machine. Everything's too expensive and they live too short to sort of get the applications up after the machine has arrived. We have to begin skating to where the puck is going to be, to quote Wayne Gretzky. So, and then demonstrate that the work of application readiness has been a fruitful activity. We need to prepare PIs to write proposals to our major application programs. And what's very, very important is to harden the supercomputer for full user applications, because the acceptance suite can never be sufficiently complete to catch all the bugs, to catch all the problems. So we need to throw at it more applications as the machine matures in order to root out all remaining bugs if possible. These are the 13 projects. They are uncomfortably long list of males, but they are applications that have been running at petascale and some that have not been running at petascale. For example, some applications here have been running on Titan, but about half of them are new to petascale computing. They include projects in climate science, several projects in chemistry, astrophysics, plasma physics, cosmology, molecular dynamics, nuclear structure physics, combustion, engine combustion, global seismology. These are some of the rather traditional simulation science fields represented by these projects and these PIs. So each of these projects was a, oh, did I come out of presentation mode? Yeah. The reason I'm pausing is because I hid some of these slides and they're not hidden now. That's strange. Okay, now we're better. So I want to say, give a few results from Summit Dev for a selection of these projects. So Bronson Messer is the PI of this. He's a computational astrophysicist at Oak Ridge, and he's studying astrophysical flames and explosions, in particular things like the explosion of a star, of a heavy star as a supernova, or the explosion that results when black holes or neutron stars would merge and produce gravitational waves. The code he's using is a community code originally from the University of Chicago called Flash, originally funded by NNSA science programs. And the current Flash status on Summit Dev is that Summit Dev provided a unique opportunity to experiment with different programming models for Flash, where OpenACC and OpenMP 4.5 have been explored. They were able to determine the optimal number for the adaptive mesh refinement blocks per GPU of production. The large memory, both the large GPU and CPU memory, allowed hundreds of blocks per MPI rank, even for large network runs. Here we're talking about the the nuclear reaction network that describes the synthesis of new elements in these stellar explosions. Determining the being able to predict and understand the natural abundance of heavy elements in the universe is one of the holy grail science projects for this area. So here's some performance numbers on Summit Dev in terms of time to solution versus a number of blocks of the AMR refinement activity. And basically the solution here says that the number, let's see, it says that the GPU can retire roughly 100 blocks at the same time as one block of the CPU. So the expansion you get in the size of problem you can do is very, very large in terms of moving on to the GPU accelerated problem. This size of problem couldn't be attempted on Titan. The memory would not allow it. So GTC is a tokamak code to solve the gyrokinetic equations for the energy transport within a tokamak, which of course is a donut-shaped fusion reactor. The PI here is from University of California, Irvine, Zihong Lin, and this is a long-standing, widely used code in plasma physics. On the current status on Summit Dev, The code already uses the GPUs effectively on Titan and actually on many other GPU-accelerated clusters worldwide using OpenACC. And the additional development work has been done to optimize that particle push for Summit Dev. The code also now uses the NVIDIA library AMGX solver to improve the performance over a PETSI field solver. And here the wall time has been shown to have a speed up of about 3x, comparing the GPUs on Summit Dev to the GPUs on Titan. HAC is the hardware accelerated cosmology code. This is a code that represents the whole cosmos, the whole universe, as a series of particles, and then evolves them through the Big Bang of the universe in order to understand the distribution of matter in the universe. The code was started at Los Alamos National Laboratory when Salman Habib was there. Habib and his group are now at Argonne National Laboratory performing synthetic simulations of synthetic skies that can be used for these large experimental, large observatory measurements that are planned for the future. This is large simulation activity, and it also has very strong data analysis activities. The test problem that was chosen for Summit Dev is basically 1,000 cube particles in a 115 megaparsec box. And it was running on 32, this configuration would run on 32 Titan nodes, one of course with each K20 processor. This thing, on Summit Dev, would take 8 nodes, each with 4 P100s. And they're getting the expected 3.5x performance improvement on the key computationally intensive routines. The last one I'm going to highlight is NAMD. It's a very popular molecular dynamics code out of University of Illinois, Urbana-Champaign. The PI here is Jim Phillips, one of the superstar developers of this code. This code is primarily focused on computational biophysics activities, and it has a large community of users, and so by porting this code, we potentially could get many applications for use in our new supercomputer. The Summit Dev work has focused on new non-bonded force kernels programmed through Cuda, new particle mesh Ewald reciprocal forces for the long-range forces, to compute the long-range forces. Explicit solvent calculations on NAMD are now 1.5 to 2.5 times faster on the GPUs. The implicit solvers simulations on NAMD are now, again, 1.5 to 5.5 times faster, and faster simulations on systems with multiple GPUs per node. Here's some data that shows roughly a factor of 2 speed up on a variety of the kernels. Well, factor of 2 to a factor of factor of 1 to factor of 2 there, and here a factor of 1.5 to a factor of 5.5, just as the notes say. Oh, yes, one more. This is QMCPAC. This is electronic structure code for materials led by Paul Kent at Oak Ridge. This is a way of solving for the electronic structure of materials that's more accurate than, say, density functional theory, but it's also more computationally intensive. But because of the Monte Carlo nature of the code, it should be well suited to massively parallel supercomputers. As they move this from Titan onto Summit Dev, they observed that Summit Dev's nodes were about a factor of 20 faster than Titan. It's actually more than you might expect. The factor 20 comes from the overall more graceful way that the memory is being managed. For example, in moving data from the CPU and the GPU, the Generation 2 PCIe bus was a very strong limit, a strong bottleneck on this code, and that's been very much relaxed. And there was a 14x speed up of the 4 P100s if you just compared to the 2 power 8s if you just limited the code to run on the 2 power 8s. So this group considers the transition from Titan to Summit, and then eventually to Summit, Titan to Summit Dev, and then eventually to Summit to be a real game changer for their science. And with that, I'll just say that we did, after working on these applications from 2015, we additionally did a call for early science proposals in December, and the idea was to open up early access to Summit to additional projects, that is, projects in addition to the ones we selected in our application readiness call 3 years earlier. A lot had changed in those 3 years, and this opportunity to provide fresh codes to come in, people who are independently preparing for the future, they were able to come in and apply to be an early user. We got 62 letters of intent. This was actually many more than we expected. They came from a variety of sources. About half of these had been running with us in the past, about half have not. And right now, these are the 60 or so teams that are getting early access to the part of Summit, basically the 25% of Summit that we accepted in December as a preliminary acceptance. They are trying to show that they can take advantage of Summit at scale right now in terms of scaling out on a large number of nodes and making effective use of its GPU accelerated architecture. They're going to write proposals for early science access that they can submit when they are ready to submit them, but we expect them to be due by the beginning of June. And the early science period will extend from the time that we accept the machine later this summer through the beginning of normal user operations in 2019. So with that, come to the end of this presentation. So Summit's still under construction. Looking for it later this year, and we're continuing to work on hardware installation and software testing. Any questions?